Welcome to the next edition of NYJavaSIG Java How Workshop. Today's topic is Java and the promise of quantum computing by our very own Burd. He is the professor at the Drew University in New Jersey. He's a Java champion. He has written many books in Java. He's also a JUG leader at NYJavaSIG and Garden State Java User Group. And he's a regular speaker, and we are very proud to have him present such an interesting topic here. So feel free to chime in, and I'll pass it on to Barry.
Please chime in. I love interaction. I love it. I love it. So here we go. Java and the promise of quantum computing. Oh boy, sounds like a good topic. Let's start by introducing it. So if you want to participate, if you want to be working during this session and take part and do some things and keep yourself busy and see what you can do with quantum computing, then you need to have Java 11. I don't know if this software works with versions of Java higher than Java 11. I've tried it with versions higher than 11 and it hasn't worked for me. That doesn't mean it wouldn't work for you. It's just that maybe I was doing something wrong. Anyway, you also need IntelliJ IDEA, either the community edition or the ultimate edition. And I really hope that you give this a try while we're going. I will stop here and there so that you can, fiddle around with the concepts that I'm talking about. Please chime in anytime and stop me and ask questions and laugh at my jokes. I really like it when people do that. Now, I'm not going to talk at all about Spring Boot. I'm not going to talk at all about databases. There will be nothing here about web interfaces, although there might be a little tiny business about graphics. There will, I hate to say it, be some mathematical concepts. Doesn't mean you need to remember math from way back, just means that it's going to look mathematical. If you feel squeamish about that, then stop me. I'll be happy to, elaborate. Okay. They always say without further ado. Well, I'm doing further ado here. I want to give a big shout out to Johan Vos, because essentially what I'm doing here is talking about his material, the material that he's about to revealed to the world in a book called Quantum Computing in Action that's going to come out in Manning in the next few months. Not only did he create the material that I'm going to describe to you, the Java side of it, but he also has graciously given his blessing for me to talk to you about it, which is, really nice. If I were him, I would have held this material closer to my vest. But he was nice enough to say, hey, yeah, Barry, go for it, do it. Explain it to people, spread the word. So thank you, Johan. If you're listening in anonymously, then thank you. If not, I'll thank you later. Again. Okay, so this is what some quantum computers look like. And if you're in a room with a quantum computer that's working, you wouldn't see this because this would be dipped in a big vat of liquid helium and kept to very near absolute zero. The thing that you see at the very bottom, that's really where the action is. That's where the qubits are, the things that are doing the processing. Everything else, all this is, control stuff, standard control stuff. The reason that this has to be very near absolute zero is because we're dealing with quantum effects. And so we're dealing with not just microscopic things, but things that are on the level of Heisenberg's uncertainty principle. And you can't mess with that stuff and not disturb it. So there's a lot of things happening that have to be kept under very strict control in a quantum computer, and cooling things to a fraction of a degree Kelvin is what it takes now. So imagine this big dipped in a big cylinder, and then you've got the beginnings of a quantum computer. Right now, the quantum computers that they have, how many bits are stored in a regular classical computer. Well, billions. They've got right now quantum computers that effectively do 50 qubits, maybe 70 qubits. It depends on who you ask and what company is trying to hawk its wares. But anyway, this is all in its very primitive state yet. And yet, it seems as if things are going to be really hot in the next decade. As a matter of fact, an aspect of quantum computing called quantum key distribution, which means distributing the keys for cryptographic communication, that's already in the works. British Telecom is already getting geared up to sell that stuff. They're starting experimental prototypes in Europe, and they know that that'll be on its way commercially available within the next year or two. Okay, what is all this stuff about quantum? Quantum supremacy. In October 2019, there was a project called Google Sycamore. And Google Sycamore was a quantum computer and a quantum lots of things. But the idea there was, is there a problem that we can solve with a quantum computer that would be really hard to solve with a classical computer, with the kind of computer that you have in front of you right now? And what they did was they demonstrated the solution to a problem of checking a random number generator, and it took 200 seconds for them. And they said that the closest classical algorithm to solve the problem would be 10,000 years. Now, the Chinese came and argued with Google and said, no, we know how to solve it in 5 days. But the point is that with quantum techniques, you can solve certain kinds of problems so much faster than you can solve them with classical computers, that it's not just a matter of, oh, it's a little better. It's orders and orders of magnitude better. With a quantum computer, problems like breaking RSA become somewhat trivial compared to the similar situation with classical computing, where those problems are almost impossible to solve. So quantum supremacy means quantum computers can do a lot better than classical computers, in theory. And they're making a lot of progress with the hardware. All right, companies that do quantum computing now actually have quantum computers on board, experiment with them, are hoping to sell them eventually, or at least are hoping to monetize their use somehow. A whole bunch of companies there, some biggies. And I have a slide here. I'm going to give a talk later on in the month. And in that talk, they wanted me to talk about careers in quantum computing. I'm not going to lie. It's not like there are lots of jobs compared with jobs in finance or jobs in almost any other industry. All the jobs in quantum computing, they're, pretty high level. And there aren't a lot of them yet. But look, average salary, $96,000 a year. It's a promising area if you're interested in being a scientist or computing research, or quantum programming. And since this is a Java group, I'm going to assume that most people here are programmers. So that's cool. Let's start then by talking about classical computing. Now, classical computing is the kind of computing that we all do. We're all doing it right now because we're sitting in front of our machines and watching me talk. All right. Strange is the name of the Java library that Johan Vos created to do quantum computing. So I'm going to kind of mix two topics in this part of the presentation. I'm going to just talk a little bit about classical computing so that you know where to focus when I talk about quantum computing. And I'm also going to show you how Strange works, maybe get you to try it. All right. In classical computing, we have bits. How about that? There's a 0 bit, and I hope you can see it kind of coming in and out at the top of the screen. Let me do that again. There's the 0 bit. It's coming and going and coming and going and coming and going. The reason I'm having it fade in and fade out is to emphasize an important point, is that if you send one 0 bit after another down the line, and it is observed one after another, if all you're sending down the line are 0 bits, then repeatedly, one time after another, after another, after another, the person who observes the bit, reads the bit, will see a 0. Well, wait a minute, there are two kinds of bits.
But are you really sending a 0 bit, or are you just not sending the signal?
I'm gonna, let me see if I can put this in the best language possible. If I line up 100 bits and they're all 0, and somehow somebody comes along and says, what's this bit? Oh, that's a 0. And what's this bit? Oh, that's a 0. And what's this bit? Oh, that's a 0. They'll see all zeros. And that's no surprise. It even sounds like a tautology. It even sounds like something you wouldn't even think about. And indeed, when it comes to bits, you don't have to think about, hey, this is a 0 bit. Do I observe a 0? But quantum mechanics is about observations and measurements. So if you send somebody a 0 bit and they receive it accurately, then one after another of those bits will be 0. And if you send them a 1 bit, and then another 1 bit, and then another 1 bit, they'll see repeatedly a 1. Now, yeah, it's just 0 and 1, and why do I bother talking about repeatedly looking at bits, one after another? Why don't I just take 1 0 and say, yeah, that's 0. You'll see that in a minute or soon. Are you familiar with classical logic gates?
Yep, we have seen that. This sounds familiar.
Okay, I mean, inside the computer, right, built out of transistors, there's a gate where, you know, if this thing is a 1 and this thing is a 1, then that thing is a 1 that comes out of it. Otherwise, you get 0. So this says, and this says, if a 1 comes in here and a 1 comes in there, a 1 comes out. Yeah, I think I said that right. Here, you're going to get a 1 if you have either a 1 here or a 1 there or both. And this thing is going to invert. So if you send in a 1, a 0 is going to come out. If you send in a 0, a 1 is going to come out. Very nice. Let's do classical computing with strange. You have Java 11, you have IntelliJ IDEA. What I invite you to do is create a new project from version control. And when you have version control, you get prompted for what kind of version control, choose Git, and then type in this URL. And I hope it's large enough for you to see. I think it probably is, yeah. GitHub.com, Johan Vos, quantumjava.git. And any directory you want to put it in, and go. I'll be quiet for a minute. Tell me when you're tired of waiting for me.
I'll post this link in the chat for people who are
Sounds good.
who like it easy.
When everything opens up, I'm hoping that you'll see something like this.
It's taking some time for me, but it's coming up. Maybe
Okay.
it's a heavy project or something.
It's probably that you're using a lot of bandwidth on this thing called Zoom.
Might be. Very possible.
How's everybody else doing? If you're not following along, that's fine. Don't be embarrassed.
Barry, can you increase your font a bit?
Mhm. I got it at 26. What's your preference? How about 32? We'll try that.
We can try that.
Better?
Yeah, this much. I mean, it's up to others as well, but I like this better than
Well, I mean,
before.
the question is this good enough?
It's a bit. I think your connection is a bit shaky because the screen is okay. I can read it, or it's
Okay.
maybe me.
All right, I'll up it just to 34 and we'll try to live with it. I'm actually not going to do much with this screen. This is just
That's
to show
fine.
you what it's supposed to look like.
Okay, no worries.
So once again, let's go back here. And so first you install Johan's framework. And once you do that, if you look at the folder called Chapter 3 and double click on the main class, you'll see code that looks like this. Now again, I'm not sure if you can read it or can you read it?
Yeah, I can read it.
Okay. Everybody else?
So,
yeah.
In chapter
So Anthony's
3,
like, yeah. This is not a real quantum computer, but an emulator. Yeah, and the way that they would take this and make it work on a real quantum computer would be to take the bytecode and write a translation for it into the assembly code for a quantum computer. It's not that this can't be on a quantum computer, it's that Johan has not done that extra step. Chime in verbally, I might miss the chat. Just unmute yourself if you like. All right, so I'm going to march on and just take a look at this program. Look, I don't want to go into depth yet about this code. I will in a minute, but basically what's happening here is I'm starting with 0 and applying a NOT gate that turns it into a 1. Wow, that, you know, talk about your hello world program. Yeah. Let's take a look. To get this to run, there's a Gradle tool button on the right side of IntelliJ. If you click that and expand the tree and go to Chapter 3, go to Poly X, X stands for not, go to Tasks, Application, double click Run. And when you do that, you'll see the helloest Hello World program run, and it looks like that. This note on the bottom tells you, hey, you started with a 0, I read a value 1. And this JavaFX display that'll pop up will be a view of the circuit. So you probably can't see it here, but this says we start off with 0, that's a little 0 there. Then we put it through a NOT gate and it ends up here. The word on is there, meaning, hey, we turned it on into a 1. So now I'm going to ask everybody, what's your pleasure? Should I pause or should I march?
So I have a question, Barry.
Sure.
So I can see when I run, I can see the Gradle screen and it's telling me the value is 1, but I don't see the blue and pink things. Is it like a pop-up that should come?
It should pop right up.
Okay.
There's a, I don't know if you can see it, but here there's this word, there's this a line that says renderer, render program.
Oh,
That's
yeah,
what-
yeah, yeah.
And if you don't see it, it might be hidden behind something else. Maybe you clicked.
Oh, hold on. I think I know why it didn't came up. Because in the actual code on Git, the last line is missing.
Oh, well, that's interesting.
So let me try that out quickly and we can
Okay.
see if the renderer is coming up.
At the end of that code, type, now you did do poly X, right?
Yeah. I did the same thing.
So
Yeah.
do renderer dot render program, parens program, and see if you get it.
I'm just trying it now.
Sorry,
Oh,
so
now I see it.
you wait
Okay.
for Gradle build to complete, right? And then you run, what is it, chapter 3,
So let me go back.
polyax POM,
So
right?
you on the right side of IntelliJ, you press the Gradle button. The Gradle window shows up, and you go down to chapter 3, poly X, tasks, application, run, and double click that, and you should be off to a good start.
So when I added the renderer line, the renderer.render program, it popped up the other thing, the
Right.
JavaFX thing. Yeah,
Isn't it nice that we can take a 0-bit and turn it into a 1?
that's pretty cool.
That's wonderful. Okay, so I'm going to march on. Stop me at any time if you don't want me to march on, or if you have any questions at all. But here we go. These are the 3 crucial steps in the execution of this program. And what I'm going to do in the next slide is kind of show you how these programs are structured. So what I'm going to do is create a set of gates. Now, just like there are NOT gates and gates and OR gates in classical computing, in this world, I'm going to use a NOT gate, that X thing, poly X. And the other gate that I'm going to use is called a Hadamard Gate, named after somebody named Hadamard. But let's see what happens here. So there you go. So first, can you read this? It says program, new program. Yes? Is the text readable?
Yes, it is.
Okay. When I create a brand new program and put in the number 2, I get 2 wires, 2 registers. And one of them is called Q0, the other is Q1. They both have zeros along them. And in quantum, a qubit is represented not just by 0, but by a line and a 0 and a little arrow. It's called a ket, that notation. And it's not going to bother us much. Just everything that we do will have kets surrounding them. So anyway, creating the program gives us these wires, so to speak, these registers, 2 registers with zeros on them. Now the next thing that I'm going to do is create a step. And this is going to be called step 0. It's a new step. And this is a step. And this thing is actually going to become part of the circuitry when I'm done. So I create step 0. And the next thing I do in this code is I add a brand new gate, just like a NOT gate or an AND gate or an OR gate. This is going to be an X gate, and it's going to be added to qubit 1 right here. It's going to be added to this point, and it's an X gate, which means it's a NOT gate. And over here, I'm adding it to step 0. So you see what I'm doing is I'm building this circuit piece by piece with each of my statements. And now I want to create another step that has 2 gates on it. Let me give that a try. So on the next line of Johan's code, I create step 1. And again, this is going to become part of this circuit in just a minute. I'm going to add a gate to it. That's this thing, this mysterious thing that I call the Hadamard Gate. And those are, mighty powerful things. But it's going to end up being added to qubit 0. That's the top qubit. That's this one over here. And I'm putting it onto step 1. Well, I want another gate on step 1. Boom. Also on step 1, I want one of these things called a Hadamard Gate. And it's going to be in the qubit 1 position. So I'm building myself a piece of circuitry, or defining a piece of circuitry. And next, I'm going to add step 0 to these registers, and then add step 1 to those registers. And now I've got myself a quantum circuit for whatever that's worth. So whole time. Oops. How's everybody doing? I know it says untitled poll, but what it says, to what extent are you understanding what I'm saying? Okay, we're looking decent here.
We have one person who's confused and wouldn't know what to ask. If you want to unmute yourself and ask a specific question, you're welcome to do that.
Yeah, I understand very well the situation where you don't know what to ask, but sometimes just blurting something out. Yeah.
So Barry, can I ask you one question while we are here? So as I understand from my knowledge on quantum computing, the traditional way of computing knows the basics are like either it's 0 or either it's 1. You know definitively that it cannot be both at the same time. So you always have one thing to be sure of. But with quantum computing, it's either 0 or 1 at the same time. So my confusion is, when you get to the logical gates, since you know what's your 0 or 1, you know the output. But how will you calculate it with a quantum computing technique when you don't even know whether it's 0 or 1? Am I making any sense, by the way?
Yeah, but we're not ready for me to answer that question.
Okay.
And I think part of my answer is going to be, that's a tough question. Okay, I'm going to start next by talking.
One more quick question. Is there any standard circuitry, or when you deal with this, you have to build the circuitry every time?
You build the circuitry every time, but it's not built. I mean, it's logically built.
Yeah.
This program, you're not telling somebody to go into a lab and put this stuff together. You're sort of creating this set of logical steps.
To solve a certain problem, it will be different for every problem, right?
Yeah, yeah.
Okay.
And when you say different for every problem, that's going to be an important theme in the next part of this talk, is that there isn't one way to apply quantum computing to a problem. And that's one of the things that makes it quite challenging.
I just imagine most people here came from a traditional background, not quantum computing. And I feel like there was no transition from an old state to a new state. We jump right into, but I hope you'll break it down.
Well, I'm going to try. I'm going to try. This is just a way of describing a circuit. This Java program or this Java snippet is just the code for describing a bunch of manipulations. In this case, just starting with 0 and 1. And other versions of quantum computing don't look too much different from this Java version. The main competitors right now in the programming space are IBM's Qiskit and Microsoft's Q#. And from my perspective, they don't look that much different from this. You kind of write a program where you're concocting a piece of circuitry and you're clever enough to know how the circuitry is going to behave, and we'll get into that soon. But I'm not. I hope I didn't sell this the wrong way. I'm not going to set it up so that you can solve banking problems with quantum computing and experiment with that tomorrow. This isn't going to work that way. Sorry. Okay? I'll try to make as much of a connection as I can. All right? Are we ready to march on?
Yes,
All right.
we are.
Okay. So now superposition and measurement. Okay, now here's where things get weird. I'm going to show you my bits slide again. And remember that this pulsating 0 means I send you a 0, you read a 0. I send you a 0, you read a 0. This one means I send you a 1, you read a 1. I send you a 1, you read a 1. Reading, the observation, the act of observing is essential in quantum computing. So now here are qubits. And remember that when I write down a qubit, I use this ket notation, physicists love it. So now there's a 0 qubit, and I create one of those by creating a new step in the strange Java framework. And to create a 1 qubit, every time I read it, I'm going to read a 1. And what I do with that is I take my step and I add a NOT gate to it. And the NOT gate reverses it from being a 0 to a 1. But the quantum world is strange. Hey, that's the name of the library. Because in the quantum world, there's such a thing as being half 0 and half 1. And what it means is half the time I read it, it's going to be a 0, and half the time I read it, it's going to be a 1. And nobody, not even nature, knows what it's going to be until I read it. So to create one of these things that's half in the 0 state and half in the 1 state, I take a gate, I make a gate, and could be a 0 there or a 1 there. I send that qubit through a Hadamard transformation. Hadamard transformation is, you can think of it as an AND operator, an OR operator, NOT operator, whatever. What it does is take an existing qubit that's in the 0 or the 1 state and puts it in this sort of half and half state. It's like the cat in Schrodinger's box that we don't know whether it's alive or dead. And nature doesn't know either. And the only way that we can know what's going on with it is by measuring it. And now I'm going to stop for a minute because that's a hard pill for most people to swallow. If you don't understand what's going on here, then join the rest of the universe, because physicists claim that they don't understand what's happening here. If I put a qubit, an electron, it's spinning, or this or that, through a Hadamard gate, then what comes out is something that is sort of simultaneously 0 and 1. And the only way to figure out what it really, really is to measure it. And before I measure it, it's neither. Here we go again. I'm going to click the 3. Sometimes it's 0, sometimes it's 1, sometimes it's 0, sometimes it's 1. Half the time it's 0, half the time it's 1. In my display here, I had it alternating, but that's not the way nature works. You get 3 1s, and then you get 2 zeros, and then you get another 1, and then you get 5 zeros, and that kind of thing. So that's the kind of bizarre world that we're dealing with here in the quantum world.
So,
Yeah.
Barry, I have a question here. So what you're saying, the second line that you have on your screen right now, we haven't observed the qubit yet. It's
Right.
just passing through the gate, right?
Yep. So
Okay.
so if there's a gate here, right?
Mm-hmm.
If there's a wire here, and we've got a 0 coming in, let's say, and it goes into a Hadamard gate,
Mm-hmm.
then what's coming out is neither completely 0 or completely 1, and it's not even in a half and half state to the point where it's kind of in between. It's something that physicists don't really know how to describe. All they can say is that half the time when we actually measure it, it looks like a 0. And the other half the time when we measure it, it looks like a 1. And apparently it's in neither state until we measure it. And that's just bizarro. I mean, it's just crazy. If I put up the poll and you say, fine, I understand completely, then you better publish it and win a Nobel Prize. I mean, it's just nobody really understands what's going on here, except that when you Hadamard a bit, what comes out is something that half the time gets measured as 0 and half the time gets measured as 1. And the measurement, the act of measuring, is part of the physics. Okay, isn't that how quantum values always are? Schrodinger's cat, yes. I would let my cat into the room here, except she thinks this room is a cat box. So I'm not going to do that. How are quantum values? Isn't that how quantum values already are? Yes. All right. Understanding that this stuff is really bizarre and unintuitive, where is everybody?
I think it's a new concept. Like for the first timers, it can be difficult to get through, but if you continue on, it takes time, but you get used to it. I would say.
You'll never in your life feel totally comfortable with it.
Yeah.
I've got somebody who says confused, and I have questions, and I'd like to take questions. Will we get the part where the benefits come from? Described uncertainty seems like a drawback.
Was it clear?
What time do I have? I have an hour and 15 minutes. I'm going to try real hard. So let me end the poll. And continue. Measurements of quantum observables can't be thought of as revealing pre-existing values. The probability of an event occurring is the frequency with which it occurs. So when we observe a qubit and we get ourselves a 0, it's not because it was a 0 all along. It's because we've observed enough 1s already, so it's time for a 0. Bizarre. Okay. A colleague of mine years ago said, quantum mechanics isn't about what we know, it's about what we can observe. It's all about observation. Now, here's a partial answer to the question, where do the benefits of quantum computing come from? If I have 3 bits, then they're in one state at a time. This is a binary 5. That's nice. Now I can do calculations on a binary 5. But now imagine that I have 3 qubits, and each of the qubits is in superposition. Each of the qubits is half 0 and half 1. Well, I might be able to take advantage of that to think of my having all 8 possible combinations of these qubits somehow in my presence. You know, this is just a 1, but this is kind of both a 1 and a 0. And this middle one is just a 0, but it's this one here, if it's a qubit and it's in a half and half state, then it's kind of like both at once. And if this is a 1 here, the same here, this is there's some information about zeroness and some information about oneness. So if I have 3 qubits and each of them is half in a 0 state and half in a 1 state, then there's a lot of stuff going on here at once. As a matter of fact, what I've got is the potential to do calculations on 0, 0, 0, or 0, 0, 1, or 0, 1, 0, or 0, 1, 1, and so on. And I can do them all at once. Now, Sergey or Serge? I'm sorry, I'm mispronouncing names. I always do it. But when we get to the part where the benefits of quantum computing come from, this looks like ambiguity to you, and I agree that it looks like ambiguity. The hard part, the really hard part of this quantum computing business is sorting out the useful answer from all the information that we have here. And the unfortunate part of any study of quantum computing is that the tricks for sorting out the valuable information from all this, those tricks are hard to find. And they vary from one problem to another. So we're not going to get, if you approach, I have a slide for this. Yeah, I don't want to jump to it right away. Where am I? All right, I'll see if I can get to it quicker than I would expect it. Let me find it here. There's a good one. The classical algorithm is a combination of generic building blocks such as loops and branches. If you give me a problem, I may be intimidated by it because it's too big, but I probably, if the problem is well specified, have an idea of how I'm going to solve it. Quantum is different. Quantum part, the part where you actually use quantum computing in a quantum algorithm comes from, it says there, discovery of a coincidental correspondence between a particular problem and the behavior of qubits. So you're really not going to get the situation where here's a problem you want to solve, and oh, I know how to do that. I just take this building block and this building block and this one and this one and this one. Sifting out the way to make order from the chaos of all these possibilities is difficult. And I guess, if you want, oh, here we go. So share the speed of calculation of 220 minutes versus 10,000 years come from parallelism. Yes. Parallelism indeed. Questions, concerns, thoughts?
So you're saying that, like, when you said 101, the first bit can be 01, second bit can be 01. So we get all these possible combinations with each and everything, with where everything is possible within these 3 digits, right?
Yeah.
That's interesting.
So let me go back to that now. If I know how to go back to that. I already do this. Superposition.
I think it was superposition and measurement.
Yeah.
Yep.
Yeah, I mean, with classical computing, you've got a 0 and a 1 and another 1. With quantum computing, each of the 3 bits is in both states at once, and physicists hate when you say it that way. But what you can do now is zap this with a laser beam, right? And somehow sift out an answer. Now I'm going to try to give you an indication of how that answer gets sifted out. I promise that you won't be satisfied with the detail, the level of detail, but I'm going to do my best. And in this case, how the value is determined. In this case, 8 states. Yeah, it's. I'm gonna show you what I'm gonna try to give you an indication of what a quantum algorithm looks like, and I'll do that in a few, since everybody seems to be itching for that. Now?
Sorry, I was talking on mute. Yeah, sounds good.
All right, yeah, okay. Now I'm going to take a guess that you don't want to do more strange right now. You'd rather see an algorithm in action. Am I right?
I can go for an algorithm. Others can chime in if they want to see something.
Okay, let's yeah, these are very good slides, and I'm going to skip them for now. Let's go to Grover's search algorithm. This is what got me interested the first time. Oh, nope, have to go back. Go to okay, now this is a thing called the block sphere. If I go back, right, I've got this slide. I just need to do a little bit more theory before I set up Grover's algorithm. Theory. Okay. Call me an absent-minded professor. Go ahead. Okay, now, why superposition is useful. So we've got this, right? Now, you know, you've got half 0 and half 1, and you can put a qubit into this kind of half and half state. And you can implement a qubit as a spinning electron. Is it spinning clockwise or is it spinning counterclockwise? Polarized laser beam. I know almost nothing about these things. I'm not a physicist, and I never played one on TV. In reality, it's not just a matter of 0 and 1 and half. In reality, you can think of the existence of a qubit as living on the surface of a sphere. Oh my God. Yeah, there's a qubit that we know is definitely 0. And there can be another qubit that we know is definitely 1. And with Hadamard, we can make it be this half and half state. But there are other possibilities. For example, We can get away without having a plus sign there, whatever that means. That would be on the other, oops, okay. I jumped ahead of myself. We can put a qubit in a 3/4, 1/4 state. And I'm going to click that again. 0, 0, 0, 1, 0, 0, 0, 1. What that means is that I somehow made it so that this qubit, 3/4 of the time when I measure it, it comes up 0. 1/4 of the time, it comes up 1. But now, look what happens when I click this next button. I can do something so that, yeah, half the time it comes up 0 and half the time it comes up 1. But in some strange way, a minus sign belongs between the two of these things. I'll kind of try to give you an example, if I can, of what that entails. I'm going to check my notes to see where I am. Yeah. The very next slide. And I promise once I do this, I can explain a quantum algorithm. So here we go. Turns out that everything has a wave nature. I know, you think you're listening to a physics lecture, not a computing lecture, but that's okay. Everything has a wave nature. So when I say half 0 plus half 1, that means there's some zeroness here and some oneness. And they're both sort of wave-like. Now, what if I change it so that it's half 0 minus half 1? Well, that's going to look like this. I'm going to invite you to keep your eye on this ball and on that wave at the same time. For something to be half 0 minus half 1 still means that half of the time I'm going to observe 0 and half the time I'm going to observe 1. But that nature has built into it this sort of situation where the wave nature of the 0 and 1 is out of phase. The troughs of one are where the crests of the other are. And yeah, I know there's no way of thinking of this as, you know, this does not happen to chairs or supermarkets or grocery stores or Bitcoins, but that's kind of the way a qubit can be. When I demonstrate Grover's algorithm, or at least talk about Grover's algorithm, we're going to have to remember that this thing, this qubit, can be half 0 and half 1, or it can be all the way on the other side of this sphere where it's kind of out of sync like this. And if I do this, I'm going to come over here into imaginary land. And if I do this, then I come all the way back to this thing, which is in phase. Let me make the little thing go all the way around the, I like doing that. I like doing that so much, I'm going to do it again. Noise cancellation, yeah. The idea here is not only can a qubit be 0 and 1 or 1, it can be half and half in a whole variety of ways. And the variety really comes from the fact that the zeroness is a wave, the oneness is a wave, and to what extent are those two waves in phase with one another? Time for polls. I don't expect anyone to say, oh yeah, I know this really well, this is great, unless you've studied physics. And I haven't studied, well, I taught physics once. But
By the way, for me, it's like I've studied quantum physics in college. It's like a nice refresher course.
I actually taught physics once, but well, I'm full of stories about that. The person who's confused and have questions, can you verbalize any of those questions?
Well, so one of the questions I have is, and I'm sorry, I missed the beginning part of this, so that could be that, but I don't see much Java in this. So is this, is this just quantum computing in general, or is there anything Java specific to this?
Well, you can do quantum computing in any language.
Right. But is this
provided that there's a framework, provided that somebody's written the code to either simulate a quantum computer or to go straight from Java bytecode or whatever to the assembly code for a quantum computer. And now, did you see the part where I did the IntelliJ, where we did that?
No, I'm sorry, I missed that.
Okay, all right. I guess I kind of, let's see. Let's do a little. Let's see what we've got here. Let's do a little Java.
That's okay. I don't want to hold it up. I can probably watch the video.
Well, this is the Java user group. Let's if you've got Strange installed on IntelliJ, then try running. Go to the Gradle window on the right side. Try running chapter 4, Hadamard, source main. Oops, no, I'm sorry. This is the project tree, and this is the code. It's basically the same stuff that we've been doing in an earlier segment. We create a new program with a step and a Hadamard gate and add the step to the program. But let's open up the Gradle window and try chapter 4, Hadamard, tasks, application, run. You're right that there isn't going to be Java in the traditional sense. I mean, it's Java code. But it's basically a Java interface to quantum concepts is what Johan's library is. And when you run this, that's what you get.
Barry, can you show the chapter 4 code if you have on the slide?
There it is.
Okay. Okay, because I don't see the render program in there as well at the end. Maybe we have to write it ourselves.
I did not have to.
Maybe they changed it. Who knows?
I downloaded this a week ago.
Oh, I see. It's there in single execution. Never mind.
There's a multiple execution and a single execution. Yes. The render program is for them to just go through this once. But when you're doing quantum computing, you don't just run something through the circuit and then say, I'm done. You run something through the circuit 1,000 times. They call it 1,000 shots. And you take the aggregate of that information and you figure out what's going on from there. So in this case, when I run this, when I'm in the Gradle window on the right side and I run this, it's just a circuit where I start off with 0, I Hadamard it, and then after running it 100 times, I find that about half the time I measure a 0, and about half the time I measure a 1. And all quantum computing is done like that. You have to do 1,000 shots, 10,000 shots to get an idea of the probability of the answer being 0 or 1. Now in this case, we got 507 and 493. That's about half a minute. If we had gone to 10,000, we'd be closer to half a minute. And 1,000 runs upon got 495 and 505. Yeah, there you go. So let's see. Where are we time-wise? 7:35. Okay. Let's do. Is it time to move on from the crowd? Yes.
I like it. I mean,
Okay.
I think people are following it.
Okay. All right. So let's do Grover's search algorithm. Now this is really cool.
Sham has a question. During the run, how do we get the correct value since 0 is for 507 times and 493 times is for 1?
That there is no correct value here because we put the thing into a state where it's half and half. That wasn't solving a problem. That was just demonstrating the Hadamard Gate. Now I'm going to solve a problem. Okay? So this is one of the earliest quantum algorithms. It's called Grover's search algorithm. And if you have 100 things and you're doing classical computing, you could take 100 steps to find the thing that you're looking for. You could be lucky and find it at first. You could find it in the middle. You can find it, but or you may never find it. But if it's there, you know that it could take up to 100 steps. With Grover's quantum search, it's going to take at most 8 steps. Which is a considerable speed up. It's not what they call turning it into, well, it's a good speed up. It's a very good speed up. So let's see how this works. So let's say that I've got 4 things. I've got 4 customers. I've got 4 banknotes. I've got 4 hats. I've got 4 of anything. And I'm going to encode them as in 2 bits. And one of the things is going to be encoded as 0, 0. Another thing is going to be encoded as 0, 1. Another thing is going to be encoded as 1, 0. And another thing is going to be coded as 1, 1. And I'm going to find this one among those. Now, bear with me. What I would normally have here would be 10,000 things. And I would have some kind of an operation that makes one of them be an outlier. And I don't know which one gets to be made an outlier by that operation. There's a function that I run that when I run it, it turns one of these things into an outlier, always the same one. And the way it turns it into an outlier is that it does that minus sign business in front of it, puts it all the way at the other end of the blocks field. So now I still have 25% probability of finding 0, 0, and 25% probability of finding 0, 1, and 25% probability of finding 1, 0, and 25% probability of finding 1, 1. But this one is somehow, you know, different from the others. This one's kind of out of phase in some bizarre way. And yeah, in case you're nervous about 25, 25, 25, 25, just there's square root stuff going on. Don't worry about it. But now I have some operation that says this guy is the one who's the guilty party. I have some function that I can apply to make him separate from the others. I just don't know which one is going to be made separate. But it's a real function. It's like which of my customers is the most delinquent, or which is the horse that won the race, or something like that. I have a function I can apply that makes this thing out of phase. All right. Get ready for some magic. Remember that I started off here with these 1/2s, and that accurately reflects the fact that a quarter of the time I'm going to read 0, 0, a quarter of the time I'm going to read 0, 1, a quarter of the time I'm going to read 1, 0, and a quarter of the time I'm going to read 1, 1. If you'd rather see a 1/4 here, that's okay. It's just square root stuff. Okay. Now, this is the situation that I've put my qubits into. I put them in a situation where they're all sitting here in the 1/2 order. Now I apply the function, and remember the function says this is the customer that I'm looking for. And when I apply that function, it takes that particular possibility and moves it to the negative side of the scale. I've done the math, and according to the math, I can zap this with about 10 gates. And when I zap this system with about 10 gates, put this stuff, these 2 qubits that represent 4 possibilities, through 10 gates, here's what the gates do. First, they find the center of gravity, where the average is. And then, miraculously, they rotate this whole system about the center of gravity. Watch it and be amazed. And now what I end up with is that the things that aren't outliers have 0 probability of occurring. And this delinquent customer that I got from applying the function has 100% probability of occurring. The probability, there's no correct. Sergio, I don't understand.
I think he meant it's probability, and there's nothing, no correct.
I'm still confused.
It's looking for a Boolean result, a probable result, so it's not Boolean final.
I'm not sure. Is there a question? Because I'm not understanding it.
No,
Okay.
sorry. I answered the Cheyenne person
Okay.
about the how when he asked how do we get the correct value.
Okay. All right. Well, in this
Probability.
case,
There is no correct.
in this case, I'm getting the correct value. There's just no doubt about it.
Oh, okay.
But that's unusual. I mean, in this case, right? I don't know if I can go back here. Let me see if I can. Yeah, so in this case, I apply the function that somehow makes one of these possibilities a negative. And then I apply gates that find the middle ground. And then I apply these magic gates that rotate the whole system and bring this to 100%. Now, the only reason that I can bring it to 100% is because there are only 4 possibilities. So I have to perform this only once. And I can actually, we can do the Java code if you're interested. I want to show you one more aspect of this, and then we can talk a little bit more about it. What if I have 3 qubits? So 3 qubits, that represents 8 different possibilities. So 7 of my customers are over here, and I'm going to just leave this 1 over square root of 8 there. Don't worry about it. And one of my customers here is, at this point, equally probable of being measured, but that customer is over on the negative side. Now, let me do the same operations to this system that I did to the other one. And now you'll see how I have to do several shots. I have to measure this many, many times. Let's go. First, I'm going to perform a quantum operation that finds the balancing point between all these, the average of all these values. The 7 of these and 1 of these. And then I'm going to do a rotation. But notice what happens when I do a rotation. Now, this fellow ends up shy of the 100%. And these end up not quite being at 0. So now if I measure this system, I have some probability of getting one of the wrong answers, and not 100% probability of getting the right answer. So what does Grover do? Grover applies the function again, putting the outlier back into the negative, finds the middle point again, and then does another rotation about 0. It's called inversion about the mean. It's called Grover's diffusion algorithm. And when I do that, I'm much closer to 0. Now, if I measure this system, if I do it 1,000 shots, I am very, very, very likely most of the time to be reading this bum outlier customer, or this banknote that I'm looking for, or this Bitcoin that I somehow discovered by applying the function. And that's pretty much the essence of Grover's algorithm. Now, how do I end up doing this, twisting around the mean? I've gone through the math, I believe it. I don't yet have a good way of explaining it intuitively. But that's kind of the way it is. If you want to do this in Java, try chapter 10, Grover, tasks, application, double-click run, and this is what you will see. The people who are feeling good always answer first. I learned this from a year of teaching on Zoom. Time to march on? Time to answer questions? Time for a sip of coffee.
Okay.
There's, yeah, go ahead.
In this example, first one you put do Grover 2, right? So you are expecting 2 as the expected result.
Let's see. Yes, 2 means that you've got, let me be really careful. Yes, 2 means that you've got 2 qubits. And in this fake situation, you're saying, I want to apply a function that's going to find 2 for me. And indeed, it does find 2. And the number of steps that it, in theory, is going to take is 1.5, but it actually finds it after 1 step. This number here, this is the number of steps that it takes in theory, and that's this number. Now, if I have 3 qubits, then in theory, the number of those twirly things that it's going to take is this. And after step 1, I've got a probability of finding the right answer of about 78%. After step 2, I've got a probability of finding the right answer of 94%. And how does it know these numbers? The answer is that what the code of Grover is doing, and you can look at it if you like, is it's doing the Grover business maybe 1,000 times. And 94% of the time, it's getting this solution 5, the solution that we targeted with our function. So
Just
my
to
office is,
clarify,
yeah.
good question. So when you run chapter 10, right? So it shows this the 6 qubit with the state, and there's nothing to adjust here. Just like, hey, it's executed, it's just showing the result, right?
Oh, you can go to the code and tweak it.
Oh, okay. But it's on the UI is nothing to adjust. It shows a final state, right? More or less. So like I'm trying to understand.
Yes. Yes.
This, the effects, strange effects that pops up. This is just a visualization of the result, right?
Of the circuit. Yes.
Okay, got it.
Oh yeah, and then you get the. Do I have that? Do I have the? Is there Yeah, this one doesn't show you a bar graph.
Yeah, it does. Yes.
It does? Okay.
Yeah, to show this percentages on a 6 qubit,
Yeah.
and okay.
Other questions or issues before I march on? I have something then of immense practicality to describe to you, but I want to wait and see if everybody's cool with everything else. Time to march on?
Go ahead.
All right. I gotta do a little bit. I gotta do a little tiny bit of, yeah. Don't anybody be upset. I've just gotta, you don't have to understand matrices to see what I'm gonna do here. You just have to kind of pick the visualization. So normally what happens, the way we normally represent a qubit in order to have some handle on the way it behaves is we write this to mean 100% 0 and 0% of 1. And then it just ends up being 0. And this thing represents 1. So that's no 0 and 100% 1. So that's this thing here. And now if you want to do half and half, well, I told you there was square root business here. So we're going to do, the equal amounts of this and this. So it's going to be like that. And now I kind of want to show you what, so this is a cube, these are qubits. This is the 0 qubit, the 1 qubit, and the half and half qubit when there's a plus sign. So this thing, then, this is the Hadamard operator. And what the heck am I going to do with that? I don't need to burden you with the details. I asked somebody today earlier if he had done any matrix multiplication, and his response was, in my nightmares. So, I'm not going to do much with this, but I just want to show you visually what's going on. If I apply the Hadamard operator to this thing, then here's how I do it. I'm going to click over here and you'll see the action over here. Right? So I take this 1 and on 1 and I kind of traverse them over here. I put multiplication signs there and an addition sign there. And then I take this whole thing and I copy it up there and I get part of my answer. And now the next thing that I do is I take the bottom part and I do the same thing. And I transfer that over here. And I get another part of my answer. And when I figure out what that is, it's half and half. So that's just to give you an idea of what it looks like to formally work with these qubits and operations. And if I go through the same business, starting with 1, well, then I'm going to get that. Okay, that just all I wanted to do was show you the visual there, because that's the basis for a very important algorithm called Shor's algorithm. Have you heard of this? Anybody hear of it?
I've heard the name, I forgot actually, to be honest.
Yeah, heard the name, yes?
Yes.
Okay, all right, here's the deal. For very large numbers, multiplying them together is easy. Finding out what I multiplied together to get one is really hard. And don't worry about this terminology, it's just geeky terminology. But the idea here is that anyone can multiply. It takes thousands of years for large numbers to be factored. And in fact, in 1994, 1996, these two people took a number like this and showed that it can be factored into this and this. And as I stare at this now, I'm not sure what they accomplished, because if they just started with these two numbers, then they could get that one pretty easily. But anyway, all right. Big numbers. Now, these are the kinds of numbers that are used in order to encrypt data in RSA encryption and other encryption schemes. So the idea is, in an encryption scheme, you tell the person who's going to send the data the values of A and B. And the person who's going to send the, you tell the person who's going to send the data the value of C. The person uses the C as a key to encrypt the data and sends it back to you. Only you know the original A and B that C came from. So encryption, strong encryption, very, very much depends on the ability to find out what these two values are, or to know in advance what they were when you created C. And going backwards from C, I can take two very large numbers, multiply them together, send them along a wire, send the multiplication of them along a wire so that they get C, and then nobody in the middle can find out what two numbers they came from. So encryption of that kind depends on not being able to factor numbers, not being able to find out what two numbers I started with to get C. Okay, now, Shor's algorithm depends on a particular feature of factoring, which I'm going to demonstrate now. Let's say, by the way, quantum computers have been able to factor the number 15. They have gotten an actual quantum computer to divide 15 and say, oh, that's 3 times 5. Okay, good. But in theory, they could do it with big numbers. So let's try to factor 15. Now, if I calculate 2 mod 15, that's really the Java symbol there. Then I get 1. This is 1 mod 15. Yeah, this is 2 mod 15. There's 4 mod 15, 8 mod 15. But then lo and behold, when I do 16 mod 15, I come back to 1, and then the whole sequence repeats. And in fact, it repeats with period 4. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. If I can figure out what that period of repetition is, then I have a good handle on being able to factor 15. And I'll show you how. First, I'm going to take the 4 and the 2. I'm going to divide them by 2. Always divide by 2. Subtract 1 and I get 3. Yeah. Then I'm going to do the same again, but this time I'm going to add 1. And when I add 1, I get 5. And wow, I've got 3 and I got 5. And when I multiply them together, I get my 15. Yeah, there are definitely easier ways to find that 15 is 3 times 5, but this is sort of a demonstration of this principle. If I know that this sequence of numbers has period 4, then I kind of have a shot at figuring out how to factor these numbers. So with that in mind, the question is, how do I find out that a particular sequence of things has a period 4, or 6, or 6 million, or 2,375,000, or something like that? Well, that's the brilliance of Shor's algorithm. There's this thing called the quantum Fourier transform. It's a matrix. And now I'm going to use a picture of matrix multiplication to give you some indication of how this can show me the periodicity of something. If I have 2 waves and they're in sync like this, then they add together very nicely. If I have 2 waves and they're completely out of sync like this, then I get flat. Somewhere in between, I get other things. But the idea is, remember that I started off with waves when I had qubits. So maybe I can arrange qubits in ways that this thing acts on this thing and gives me a number that is the period of repetition. So here's what I'm going to do. And this is purely graphical. There's, and it's not terribly accurate, but it'll give you an idea of what's going on. Here's something that's of period 4. I want to discover that it's of period 4. I want to discover that. Okay? So what I do is, in this matrix, I somehow arrange my numbers so that there's a sequence that repeats twice, and another sequence that repeats 3 times, and another sequence that repeats 4 times, and another sequence that repeats 5 times. I'm not doing justice at all here to Shor, but I think I'm going to convey the idea here. If I do the same kind of thing that I did with multiple matrix multiplication, when you add these 2 waves together, you get something ugly like that. When you add those 2 waves together, you get something equally ugly. But when you take this period 4 wave and you compare it with this that you don't know, because you're trying to discover this, when you add that to your period 4, your existing period 4 wave, you get this great, wonderful pattern. And that's how you identify the fact that something is repeating with period 4. And once you've got the period of repetition of these numbers, you can use it the way I showed earlier, kind of, to do factoring, right? If I do this, yeah, still same garbage. But you notice what's happened here is I started off with something I wanted to discover the period of, and I applied several possibilities, and one of them ended up standing out. And that is, in fact, the underlying idea behind Shor's algorithm. And if you want to see the Java code, yep. Chapter 11, quantum factor, tasks, application, run. We need to factor 2,336. We do some calculations. We find a period of 36 with the quantum Fourier transform, and we get 16 times 146. Now, these are tiny numbers. If we used really large numbers, regular large numbers, we'd go nuts. I mean, this would bring the classical computer, the simulator, to its knees. It wouldn't work. And there are no quantum computers yet that can do this kind of operation. But this is a proof of concept, at least. And if Johan, some person who's contributing, takes the string system and translates it into assembly code for the IBM quantum computers, this can be run on a real quantum computer. And now I'm going to be quiet, which I seldom do, and ask what kinds of questions you might have. And I was pointing to this, and I was in the way of it. I'm going to get myself out of the way. By the way, we're raffling off IntelliJ. I don't think we announced that. Neha, did we?
That was supposed to be surprise, but yes.
Oh, okay.
I'm just kidding. I don't know.
Not supposed to be a surprise. It's supposed to be something that keeps people listening.
Yeah.
Questions? Anybody have questions or responses? Anything? Kudos.
So,
yeah.
Technically, first of all, kudos. Technically, we can take this code, convert it into an assembly level code, and run it on a quantum computer, and we'll see the actual time difference, which will really make us think, okay, this has gone way too fast.
Right. Now, the problem is that the current, look, when you've got something, when you've got a qubit in this half and half state, these qubits are delicate beyond imagination.
Right.
And so, first you supercool them. super, super, super duper cool. And then you still have trouble controlling it. So at the moment, they've gotten to be able to control about 50 qubits at once. And that means that they can factor 15, which is a proof of concept start. But it's not something that we could make use of yet.
Okay. Is that why it's like you mentioned at the beginning, it's like kind of tipped in helium, or I forgot what exactly was at the end of the quantum computer. Is that what it is, trying to cool it down?
Well, yeah, you cool it down so that you can get more control, so these things don't, change as quickly. So that they,
Got it.
Yeah.
Interesting.
And I mean, the technology is advancing. There's promise of being able to do this with more and more qubits in the next few years. At the moment, the only way that they can create a qubit is by creating about 10,000 of them and measuring the sort of aggregate response of the qubits. So those are called logical qubits versus physical qubits. But anyway, that's what they're doing. Yeah, anyway, I imagine everybody's going like this right now.
Anyone has any questions for Barry?
Carnot maps meet linear algebra. There you go. So, yeah. That's my story, and I'm sticking to it. And I'll turn it back to you.
Very cool.
You can heap praise on me, and then we'll do our raffle.
I think there was someone who was trying to speak. I don't know who was it.
It was me, Todd Foster.
Yeah.
Hi.
Very cool. Thank you for speaking.
Yeah. Thank you.
Great stuff.
Yeah. I love this stuff. But, I'm weird, so.
No, you're not, Barry. So thanks a lot for teaching us about the quantum computing and Java. It was such a refresher course for me, at least. I love physics, and quantum physics is one of my favorite topics because it makes me engaged with the technology and physics and science. So it was very interesting for me to learn how the two of my favorite topics connect with each other, Java and quantum physics. So that's very nice of you, Barry, to show us this slides and introducing us to Strange framework and being able to run something on ourselves, which is the most interesting part of the interactive workshop here. So thanks a lot. I think we should start with raffle, and I will hand it back to you, Barry. Barry is also our producer and director, sort of. So
I'm the raffle master. So I'm going to go to another slide. And what we're going to do is, in the chat, you get to type in a number between 0 and 29. And I guess we have two. Rodrigo, how many intelligent? We have two, right?
Yes, that's right, Mary.
We have two. So the two closest modulo 30 are the winners. And you can send your email to us privately in the chat if you win. But everybody gets to type in a number, and we'll wait just a minute for that number to get typed in. Everybody type in a number. What you win is a full IntelliJ license for a whole year. A JetBrains package, I think it is, right?
Yep. It's for the entire products. You can use it for not just IntelliJ, other products at JetBrains as well.
Yeah, and now it says, who can see your messages? The answer is, remember that on Zoom at the bottom, there's the bottom of the chat, there's a little thing that says everyone. Well, if you don't want everyone to see your email address, you can address it to Rodrigo, yeah?
Yeah, we can email you to info@javasig.com.
Oh, info@javasig.com. Oh, that's
Yep.
my email.
I'll type it in.
Okay.
Here you are.
Okay, all right, are we ready?
I think we are ready. We have people typed in numbers.
And I'm just looking over the people who are present and wondering, first of all, am I in the way of the wheel? Yeah, I'm in the way of the wheel. I don't know if
How are
anybody.
you moving so fast?
Oh, I'm
Yep.
very. I don't know if anybody will recognize the music that comes along with this. I got music now.
Are you playing? I didn't hear it. Oh. What is it from Wheel of Fortunes?
No, you can hear it, right?
Yeah, I could hear it now.
Did anybody recognize that?
It's number 19 it has stopped at number 19, right?
Yep.
Okay, Barry, I think the wheel is inverted, but I can.
Yeah, 19.
Yep. So who's the closest? We have 17. 2 people are at 17, I guess. That's the closest. Oh, one is 22. That's more close. Oh,
17 is closer, right?
yeah, 17 is closer.
Yeah, we have 217. So
Yeah,
there you go.
There you go. 2
All right.
licenses to number 17.
Send your email address to info@javasig.com or javasig. Yes, info@javasig.com.
Congratulations.
Go. All right.
I like the IntelliJ license thing because I won it at Chicago Java User Group. It's so nice.
I used to win things all the time, and now it stopped happening for me. So I'm envious.
You'll get there.
All right. Okay. Neha, back to you.
Okay, thank you so much for coming to NYJavaSIG Java How workshop. Remember to sign in. You can go to our website. Remember to follow us on Twitter. We are always active on Twitter and on our website. We keep updating, having new sessions every month, and we have Java How interactive workshops as well. So remember to keep us aware and joining. Thank you. Yes.
Thank you, folks.